Now we'll be looking at one of the important topics or areas of mechanical wear of materials, that is fracture. Why is it important? Because when material fractures catastrophically, it may cause loss of life, and thus we want a material to serve its full time and doesn't disintegrate or fracture catastrophically. And thus it is very important to understand how material fractures. Here there are some of the cases which I have shown where material have or different materials which are subjected to different conditions or atmosphere, they have fracture or they fail to perform during that service conditions. So here an example of Aloha aircraft where you can see the fuselage of this airplane has disintegrated in mid-air and caused some lives also. Here there is an example of Liberty ships which were used in World War II, and you can see the hull of this Liberty ship were broken in between. And here there is a bell, that is a Liberty bell, where you can see there were an unsuccessful attempts to breach this crack, and thus that this bell, since it has been made, it has been not used. You would have been knowing this example of Titanic where it hit to an iceberg and causes or it sunk because there was a fracture on the hull side and the water entered and it sunk. Here in this case, this is also example of Space Shuttle Columbia where it disintegrated in the mid-air and all the crew members or engineers died. So here in this case, a refractory tile from this Columbia shuttle was detached and it got hit on a wing, and that causes some flaw to be developed, and when this Columbia shuttle entered into an atmosphere, it caught fire. You can read about all these cases on internet and get more information about all these cases. And important point which I would like to mention is that as a material scientist, we have to stop these catastrophic failures, and thus we need to understand how fracture occurs. Let me give some historical perspective when I'm talking about the strength of material, which may help to prevent fractures. So here, Leonardo da Vinci conducted an experiment. In that experiment, he put a sandbag or hung a sandbag at the end of this wire, and what he did that in those experiments that he changed the length of wires and he kept the weight constant. And when he plotted strength versus wire length, what he found that strength decreases with an increasing the wire length. That means this wire demonstrated a higher strength or stress as compared to this wire, which has a higher length. And what he concluded from these experiments is that the smaller wires has less number of flaws, and this is a very important point. So smaller wires has less number of flaws as compared to larger wires, and thus these wires demonstrated a higher strength as compared to these larger wires. In general, we can say that bulk materials demonstrate a lower strength as compared to a material which is in the wire form. This you can say that effect of size on strength. So you can say that flaws in the material will lead to a lower strength, which will make the material to underperform. So here in these lectures, when we are dealing with the fracture, we are looking at such kind of flaws. Let's move on and understand what exactly fracture means. So if you want to find out a definition of fracture, you can simply say that it is a separation of objects into two or more pieces, or I can say disintegration of objects into two or more pieces. Let me explain fracture by using stress-strain curve, which we have seen many times. So we know that when you subject a material for a tensile stress, you can say that material deforms elastically, then plastically, and then it fractures. So such kind of stress-strain curve is demonstrated by ductile materials that demonstrate a large plastic strain, while another materials like this which doesn't show any plastic strain. This material is called as brittle materials, which they don't show any plastic strain. So in ductile materials, you can see that materials deform elastically and then it enters into plastic deformation and then it fractures. So this cross is indicating a material is failed or fractured here. While in case of brittle materials, you can see that materials deform elastically. As soon as they try to enter into plastic region, the material fractures. So this kind of behavior is shown by metals or thermoplastics, and this kind of behavior is shown by ceramics, concretes or thermosets. Here in this case, when the materials deform in a ductile manner, the yield strength and ultimate tensile strength are different. Let me explain it to you. So here you can say that the yield strength is somewhere here and the tensile strength, ultimate tensile strength is somewhere here. And you can say that there is a difference between yield strength and ultimate tensile strength. However, in this case, you have elastically deformation till this region, and as soon as it enters into plastic region, it fractures. So you can say that the yield strength and ultimate tensile strength are more or less equal. This is what it means. And here in this case, you have large amount of plastic strain. So this large amount of plastic strain after yielding has occurred. So this kind of materials are majorly plastic, while these materials are majorly elastic. Now let me explain it to you how the material deforms during a tensile test. So here you have a sample which has been subjected to force, and as you see that there will be some planes which experience a maximum shear, and that's because of influence of this stress, the shape change will occur, and there will be a formation of neck, and there will be a reduction of area and which causes geometrical softening. And at the end, you can see that as material keeps deforming, the material will disintegrate into two pieces, and thus the fracture happens. Now, based on this fracture surface, which we obtained during uniaxial tensile test, we can say that what can be a nature of fracture or nature of material also. So let's look at some of the geometries of fractured samples. So here in this case, the area is much narrow, as much as equal to point. So such kind of fracture is demonstrated by ductile materials. While there is no change in the cross-section or area here, you can see that almost there is no change in the cross-section area. This kind of fracture is demonstrated by brittle materials. However, in this case, which shows a fibrous fracture, these are moderately ductile materials, which lies between ductile and brittle materials. Now let me give you practical examples. So here I have shown fractured samples or fracture geometry of two materials. This is for aluminum, this is for high strength steel. And here aluminum shows a cup and cone ductile fracture. So mostly all ductile material shows cup and cone failure. Let me explain it to you. So this is kind of a cup which you can see, and this kind of a cone. So all ductile materials demonstrate such kind of cup and cone ductile fracture, whereas brittle fracture happens with no change in the cross-section area, almost no change in the cross-section area, and thus they are relatively flat. Now let me explain you how ductile fracture occurs during this tensile test. So here you can see there is a neck formation, and thus there is a decrease in the cross-section area, and the stress will be concentrated in this area. And because of that, there will be formation of voids, and these voids will coalesce after a certain time, or if you keep deforming the material, and this coalescence will lead to formation of cracks, and these flaws or crack act as a stress concentration regions, and thus if you could go on continuing the deformation, that will lead to a failure or a fracture of this material. So you can see there is a fracture here. So you can see this cross-section area where you can see there is a fibrous nature of this fractured surface, which indicates that the material has started or started deforming in a ductile way. However, the shear, that is a flat regions, which indicates as soon as this coalescence occur, there is a formation of crack which propagates catastrophically and thus leads to a fracture of this tensile sample. Now let's look at some of the SEM micrographs. So for a ductile material, you can see such kind of voids formation, and these voids are called as dimples. This dimpled surface indicates the material would have failed using in a ductile way. While you can see that in a brittle fracture happens with more or less no change in cross section area, and these will be relatively flat features which you see in a fracture on a fractured surface. And this kind of fracture occurs catastrophically. So there will be some kind of micro cracks which will be present, and when you apply a stress, these cracks propagates catastrophically, and thus you see such kind of features. Now based on this fractured surface, you can find out what can be the conditions or operating conditions. So these features will help us to identify what can be the operating conditions of strain rate, temperature, or stress state, or some corrosive atmosphere were present or not. So it is very important to understand how fractured surface analysis has been done. Now let's move on and try to find out what is the stress that is needed to disintegrate material into two pieces. So that we'll be calling it as theoretical cohesive strength. And when I want to find out theoretical cohesive strength, I am using it for brittle materials. So what are brittle materials? So they are majorly elastic. So as soon as you try to enter into plastic region, they fracture. So we are trying this for brittle materials. Now to find out this theoretical cohesive strength, what we do is that we use this energy versus X plot using a Leonardo Jones potential, and you can see that the energy variation when we try to bring out two atoms close to each other, this energy will vary in this fashion. We all know this. Let's consider this minimum energy which is being achieved when atoms are close or in equilibrium separation. Let's call that separation to be x naught. Now what we want to find out as a theoretical cohesive strength, that is we want to find out a stress at which the material will break. So let's do that by moving these atoms away from each other and try to find out what can be the x that is needed to disintegrate material or to break material. Let's consider this as to be x when at x distance. When you stretch it at x distance, the material will try to disintegrate, or we are trying to break these bonds. Now what can be the force that is needed? So how you identify that force? By just simply taking a derivative of this energy plot with respect to x. So you find out force by taking du by dx, and you get this force variation with respect to x in this way. So at x equal to x naught, you have force variation to be 0, and at certain x you get a maximum force, and after certain x the material will disintegrate. Now what you can consider that this force variation with respect to x to be vary in a sine way. So I consider this force variation to be in a sine way. This is just an approximation so as to find out what is a theoretical cohesive strength. And this assumption remains valid for most of the materials. And I call this distance, that is, if I move x by lambda here, I can say that the material will fail at this location of x. And this is a maximum force or a critical force that is being needed, which I have to cross so that material will fail. Now I can formulate this force with respect to x using simple sine function, and let's consider these scenarios. The first scenario is like you apply a force and the equilibrium distance is x naught, and then you increase the force in such a way that this x becomes greater than x naught. Material is getting pulled away, and when x equal to x naught plus lambda, that is this complete distance from this here, it is x naught plus lambda, and material will break at this third scenario. Now let's find out what is the variation of force, and that force is given by, you can write in terms of a sine function, that Fc is nothing but this is a maximum force or a critical force, and you can write it as sine pi x minus x naught upon lambda. This is how the force variation you can find out by simply using this force variation of x, or considering this force variation with respect to x as a sine function. And let's consider this x minus x naught is much smaller, so you can write this f to be, or approximate this f as fc pi x minus x naught upon lambda. Now you can convert this force into stress just by assuming that this is, you are applying force on certain area. Here I am marking over here, so we can consider this as to be an area, and we can consider that we can convert this force into stress, and we are considering this for a brittle material, so there is no change in area as such, so you can consider this area to be constant. So if I divide it on both sides by area, I can write this as sigma equal to sigma c pi x minus x naught upon lambda. This is a somewhat valid approximation which we can use. Now we can write strain to be x minus x naught upon x naught. So from this relation you can find out what can be the strain. So you are stretching by x, and original length is x naught, and you divide it by original distance, and you can find out what is the strain. And now what you can do is that you can plug in this x minus x naught using strain and this x naught. So we are going to replace this term, and when you do that, we get sigma equal to sigma c epsilon x naught pi upon lambda. We can replace this sigma upon epsilon by Young's modulus. Let me write it down. Sigma upon epsilon, you can replace it by Young's modulus, and when you rearrange these terms, you can find out a maximum stress or a critical stress in terms of Young's modulus, lambda, pi, and x naught. So this x naught can be obtained, that is equilibrium separation between two atoms, can be obtained using XRD data or some other evaluations where you can find out what can be an equilibrium separation between two atoms. So you can find out interplanar distance, etc., and we can get this term. We can find out Young's modulus too, but finding out this lambda becomes difficult. So we need to find out a way by which we can measure this lambda, this distance, this lambda, and thus so that we can predict what can be the theoretical cohesive strength of a material. And to do that, we'll be looking at in our subsequent slide. So we have this relation sigma c is equal to E upon pi lambda upon x naught, and we know that there will be two surfaces which will be created when we have a fracture. Let me explain it to you. We have marked this as one area, so we have these two areas which has been created when we have fracture of a material, and this area will be associated with some amount of surface energy. Let me mark that also. It will have some amount of surface energy, and we can write that the surface energy per unit area as gamma, and we can say that what can be the work done. The work done is to create this surface energy, and we can write it as 2a into gamma. So it will be energy, which is nothing but a work done that is being required to form these new surfaces. And we can correlate this work done by finding out what can be of energy that is being put into material to generate this new surface, and that can be found out by integrating this force which we need to cause certain displacement. And we integrate from x naught to x naught plus lambda, and we can find out this relation as, if you go and check in the previous slide, you can replace this f in terms of fc and this relation, and you will end up in this relation where you have 2a gamma equal to 2fc lambda upon pi. If you solve this integration, you will end up in this value, and you can get this relation, and where you can put this gamma, that is surface energy, to be equal to sigma c lambda upon pi. So you bring this a here and you convert this fc upon a to be sigma c, and thus we get this surface energy to be equal to sigma c lambda upon pi, and this lambda we can find out from this relation to be pi gamma upon sigma c. Now what you can do, that this lambda you plug in into this relation, and you get sigma c equal to e upon pi 1 upon x naught pi gamma upon sigma c. Now if you bring this sigma c over here, so it becomes sigma c square e gamma upon x naught, and thus you can get sigma c is equal to under root of e gamma upon x naught. And if you look at all this equation, you can find out E by using tensile test. You can find out x naught using X-ray diffraction, thus by measuring interplanar spacing, etc. And you can find out gamma, that is surface energy, using experimentally or using some theoretical calculations too. So we can find out what can be, or we can approximate what can be a theoretical cohesive strength for a materials. Mind you, this is for a brittle materials. So this is a cohesive strength of a material, and let's use this relation to find out or estimate what can be a cohesive strength of silica. Silica is a brittle material, and let's get some of the values like E, gamma and x naught. So for silica, the Young's modulus is 95 GPa, gamma is something around 1 joules per meter square, and x naught is 0.16 nanometer. And when you use this relation, what we find that sigma c is equal to 24.4 GPa. So you get this sigma c, which is much higher, and this is not much higher. This is almost 2 to 4 orders of magnitude higher than the experimental values. So for the cohesive strength of silica, that is a stress required to break or disintegrate silica, is much lower. That experimental stress which we observe is much lower than what is being predicted theoretically. So this is a puzzling question, and we'll be looking at why the experimental values are almost 2 to 4 orders lower than theoretical predicted values in the next lecture. With this, I'll stop here.